Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our February webinar, Retrofitting Existing Pipelines for High Fidelity Distributed Fiber Optic Monitoring. And we're very pleased to have as our presenter the President and CEO of Hifi, Steve Koles, who, when he isn't working at his day job, also serves as the Treasurer of the Fiber Optic Sensing Association. Steve, we really look forward to hearing your presentation. Thank you.
Thank you very much, Mark. Appreciate the introduction and appreciate the opportunity to speak. We're very excited about this topic and look forward to talking more about retrofitting existing pipelines for distributed fiber optic sensing. What we thought we'd try to cover off today, first we'll start with just a little bit of background on Hifi, and we'll talk a little bit about concepts of distributed fiber optic sensing specific to pipelines and more specifically, preventative pipeline leak detection. We'll then go through a little bit more in the way of deployment methods. We'll talk about these more generically to get a better context. And then we'll apply a couple of those different deployment alternatives to how we can use those to retrofit pipelines. And we're going to do that both external to existing pipelines, as well as retrofitting internal to existing pipelines. And then we'll talk a little bit about sensing performance and data examples of what actual sensing looks like with those two different types of retrofitting models, and do a bit of summary at the end. Now, it's interesting, most of the FOSA webinars we've done to date are quite technical and very based on optical sensing. Today will be a little bit different. We're actually going to talk a little bit more about construction type of activities in and around pipelines than maybe you've seen in the past. And hopefully that'll provide a little bit more context for some of the things that FOSA members such as Hifi need to be mindful of as we deploy our technology. A little bit about Hifi. We've been around since 2007. We had our head office in Calgary, Alberta, Canada. We are a fiber optic sensing technology company and a proud member of the Fiber Optic Sensing Association, even before I was on the board and treasurer. We have quite a bit of energy experience and focus on providing a turnkey, high fidelity distributed fiber optic and optical sensing system. We're also quite engaged in our own system hardware, as well as software development in artificial intelligence and machine learning, as well as graphical user interface as well. Through that, we're quite proud to have over 60 patents, including 2 new ones that we announced earlier today. And as our name suggests, we're very focused on high quality data. Some of our background also includes strategic investment from Cenovus Energy, Enbridge, obviously a large pipeline company, and more recently BDC in Canada. And with our investor focus, it's also aligned our focus to be very oriented around pipelines and pipeline safety. We've been around and using our technology sensing in oil and gas, dating back many years on a downhole deployment basis, where we really hardened the technology, but then have been able to evolve the technology to be very focused on our marketed names of high fidelity distributed sensing, or HDS, and our control room software and how that applies to an end-to-end solution for pipeline operators. Also very proud to be named innovation winners for a previous Global Petroleum Show, as well as the Canadian Energy Pipeline Association. So we are very focused on pipeline sensing, and while we are very much a technology service-based company, we've certainly had to learn much about what it means to be a pipeliner, and including all the different complexities of trench and trenchless based construction techniques that are used for pipeline deployment. And you're going to see a lot of that mentioned in today's presentation. I guess I said it wasn't going to be a technical presentation, but I do start with a slide that we've done on some of the other webinars we've done, just to talk a little bit about high fidelity and approaches of managing the challenge of controlling light and maximizing fidelity, or really signal to noise ratio, particularly over long distances. We always want to be respectful of our other FOSA members. There are multiple approaches to optical interferometry. Most or many FOSA members use backscattering technique, which we believe is actually quite acceptable and very well positioned for certain applications across various industries. Hifi actually started using backscattering in conventional DAS and DTS well over 10 years ago. However, as we focused on pipelines, we simply didn't believe it had the applicable sensing performance or fidelity required for that focus on pipelines. And as a result, we've worked on a different approach to interferometry. So instead of using backscattering, Hifi uses a low-angle fiber Bragg grating reflector, or FBGs, along with dense wave division multiplexing and time division multiplexing, DWDM and TDM. And we use those to manage and reflect different wavelengths of light. Now, typically FBGs have been used as more of a point sensor, measuring spectral shift in the FBG, making it a point along a measurement. But FBGs can also be used as in other ways, namely as a wavelength dependent reflector, where the approach to interferometry is what Hifi is taking. The result is a fully distributed sensing platform in very high fidelity or high definition, and very, very well suited for long distance sensing, which helps Hifi be better positioned for what we're trying to solve in terms of problems with pipeline applications, pipeline integrity, and pipeline safety. And what are those problems? Those are really simplistically space and time, over 100% of a long distance. The industry has been challenged for years on having and needing more advanced sensing capabilities and technologies. Conventional approaches that pipelines will use for monitoring and leak detection could be a variety of different point sensors. That can include calculations of mass balance between things like flow meters, microphones and geophones, cameras, infrared technologies. They also use periodic surveys, whether those are on top of the pipe, near the pipe, inside the pipe, through a variety of different inspection methods, all of which are great and should be used as part of pipeline safety and monitoring and management. However, all of these have the challenge of not being at the right place at the right time should an event, and this picture showing obviously the worst type of event we could imagine, with a rupture. If you're not at the right place in the wrong time, you'll always have this doubt. You'll always have this lack of assurance, and we can't get there until we can get to 100% coverage and to get closer to 100% assurance on pipeline monitoring and ultimately the safety objectives being met from that pipeline monitoring. So enter the world of using specialized fiber optics as a high fidelity distributed sensor. So we, like others, have a capability to be able to sense different levels of energy coming off the asset. We believe it's actually quite key to be not just fully distributed, but also fully integrated at a system level for what we're sensing on a pipeline, and do so in as much high fidelity as possible. So as a result, we're able to sense through our specialized sensor fiber platform changes of energy. And so that energy could be thermal energy, it could be acoustic energy, or it could be kinetic energy, movement, vibration, and strain. We can do that all in very, very high resolution, which applies very well to pipeline applications. Breaking down a little bit more about our technology, there's really three main integrated categories for what is Hifi distributed sensing, or HDS. It does start with the special fiber optic sensor that is designed for high fidelity sensing and is deployed along the length of the pipeline in terms of the location of where the sensing is desired from the pipeline operator. And we're going to talk a lot about how that gets deployed here throughout the rest of the presentation. Signals and data coming from that sensor then get processed by the system hardware. Typically along a pipeline, this is going to be located in a pump station or potentially a hut for a valve. Some location where we have good indoor location power and then can leverage communications. In here, we have a significant amount of horsepower that are using computational resources to process a lot of data. A 100-kilometer pipeline for us can generate upwards of 10 terabytes of raw data a day. And so being able to leverage concepts like edge analytics and ultimately processing hardware that is out in the field close to the asset is what is required. And then the final category of our technology is really the software. And so as I'd mentioned, we are running a variety of AI and machine learning based algorithms, both supervised and unsupervised, to provide monitoring, leak detection, event detection of other type of events or flow anomalies. And as those events are detected, data is pushed to what we call the HDS monitor user or control room interface software, which is a web-based platform can be individuals or analysts sitting in their office or at home, or more widely used on larger screens in control room type of environments. So that's a little bit about Hifi, a little bit about our technology and our approach to providing that technology to pipeline safety. Let's talk about being in the field and how we actually deploy that technology. So really, there are three areas of deployment that we're focused on. What we call on the pipe or external on the pipe deployment. This is where we're deploying the fiber sensor in an electrical conduit. We'll talk about that a little bit more in a moment here. Typically empty, meaning the electrical conduit is placed empty during construction. And then we can inject a variety of fiber optics, sensing fiber and telecom fiber into that electrical conduit, because it's a very effective and low-cost way of providing safety and monitoring capabilities during a construction-oriented technique. We also have then near the pipe deployment. Now we're going to talk a little bit about this in terms of how that can be placed close to existing pipelines, and so that becomes a big part of the retrofit strategy. But there can also be elements where we have multiple pipelines in a common trench. And so instead of placing fiber on every single asset, we can actually just be near multiple assets at the same time, and again, provide an effective monitoring platform. And then finally, and we'll talk about this quite a bit, is the whole notion of internal deployment, taking that fiber sensor, typically first preloaded into a stainless steel capillary tube, and actually deploying it inside the pipe, where we will actually monitor within the flow of the pipeline, which is very similar to sort of downhole wellbore applications for oil and gas. And again, very effective way to address existing pipelines. So these bottom two categories are where we're going to spend most of the rest of the presentation talking about how we can use approaches in construction and deployment to actually retrofit existing type of pipelines. Now, first, just to provide a little bit of context, I got lots of great pictures here to show. This is an example of on the pipe external deployment examples. Again, that orange electrical conduit is deployed typically on the 12 o'clock position of a pipe, where it's a single pipe in a trench. And these are open cut examples where it's very incremental activity to be able to place that conduit along with the pipeline asset, and again, very economical in doing that. We've been doing this for many, many years. Near the pipe external deployment examples can be, as I was describing, where there actually may be multiple pipes actually in a common trench. And so to monitor, in this case, we've got a heavy oil line and a diluent return line. Monitoring both, given we need be effectively around a meter away from each of these assets, we can actually place that same electrical conduit down the middle of the trench in between these two assets, and then provide an effective sensing for both pipelines at the same time. We also have images here where we actually would terminate this electrical conduit into what are called handhole vaults. These can be buried at grade, as these pictures are showing, or they can be buried much deeper along with the pipe, depending on the depth of cover planned for the pipeline itself. Now, I've talked a little bit about electrical conduit here quite a bit. We're often asked why we prefer using electrical conduit instead of using outside plant rated or direct bury type of cables. I should point out we are partnered with another FOSA member, Duraline, where we do use a multi-microduct electrical conduit. So this orange conduit that you see in these pictures actually has, in some cases, 2 or even more microducts that we can use for various injections of cables. Why we use the electrical conduit is sort of many aspects to it based on our history. Number one, we just find that it is the most versatile to support all the different types of deployment methods out there that are trench or trenchless based. Those pictures I showed a few slides ago of the open cut are nice and pretty and look very easy, but pipeline construction is typically much more complex than that. There's all kinds of methods where there's either directional boring or drilling. We have examples here where we've got cased pipe, what's called direct pipe, concrete coated pipe, or examples where pipe is actually going into swamp areas and bag weights are being used for buoyancy control. All those actually allow us to use conduit in a much more robust way than using direct burial fiber. It's easier to deploy empty conduit during an active construction site than having fiber optics in the middle of construction contractors. So it's much easier to deploy empty conduit and inject at a later date, either immediately later or even years later. It's really about future-proofing that pipeline. We've also found it's easy to repair or remediate if future issues do occur. We've had the unfortunate incident just a couple of weeks ago, actually, of construction activity digging in and cutting a conduit and the fiber. If that was a direct burial cable, the repair aspect of that becomes much more complicated than repairing a section of conduit and, frankly, injecting new fiber cable into that section. It also permits multiple different types of cable deployment. So I talked about using our specialized sensing cable as well as telecom fiber. We have many pipeline operators that are deploying either for internal purposes or otherwise, upwards of, down as low as 24-strand cables, even as high as 144-strand cables in the extra ducts that exist. What's nice about that is that conduit structure can be accessed or reaccessed for future innovations. Think about 10 years from now, if there is a new engineered specialized cable that has that much more high fidelity, those existing ducts can then be reaccessed and redeployed. We also can use this conduit for multiple levels of redundancy. You can actually see on this example here, we have a directional drill with a pipe being pulled into a borehole, and we've actually got multiple levels of electrical conduit here just to provide additional redundancy. And then finally, what we've actually found is the specification of the microduct that we're using actually does maximize signal to noise ratio for our specialized fiber. So it does always come back to us being able to provide greater level of data quality. Now, as it relates to cable or conduit placement, it's very important to understand the dynamics of the energies around various pipeline events. Now, I say events, obviously the worst type of an event that we frankly don't even want to see, but we want to detect if it does occur, is a leak event. And that's what we're going to review here on this slide here. Hifi has tested all kinds of different sensor positions, whether that's a clock angle or distance from the pipe, to determine where the most optimized location actually is for sensor deployment. This is all very relevant for retrofitting. We've detected low-level leaks with conduit or fiber sensors even 3 meters away from the pipe. But given how dynamic conditions can be in the environment and all the different variables that are in play, we really can't rely on that distance to be that far away from the asset that we're monitoring. Now, if we review the dynamics of a liquids-based leak, which is what we're doing on this slide here, around a pipeline, gas and multi-phase type products may be a little bit different. The actual signatures, the energy signatures and data signatures that the Hifi system is looking for really starts with a rupture impulse, which is really from the change of pressure from the pipeline as a leak event actually starts to occur. Now, this may include a negative pressure pulse, but it may not. It all depends on product type and a variety of other factors. After that first rupture impulse, and that can actually even be very, very low level leaks providing that first impulse, we then look for the signature of sustained acoustics. Obviously, when we have product flowing from the leak orifice itself, it's going to sound like a leak, and picking up those acoustics then become very, very important element of it. Then you'll actually start to see a thermal change, and this is really as product begins to seek the least path of resistance and starts to migrate around the pipe. Even if that orifice is, say, on this example here at the 9 o'clock position, it'll start working its way around the pipe through microannulus. And then over time, we actually then have heave-based strain on the pipe from really the in-situ saturation of, in this case, a liquid-based leak. Now, we've learned through hundreds, literally hundreds of sense leaks that on the pipe, so this orange level here, sensor position is the best, certainly from the perspective of a new build, but as well as from a near field perspective, being close to the top of the pipe, just off, maybe around between the 2 o'clock or 10 o'clock position. We'll call it 3 o'clock position. And then the other effective area then become internal placement, or going inside the pipe to be able to pick up all these different energies associated with this type of liquids leak. Now, every field situation and deployment are different. There's all kinds of variables in the environment. And this is why pipeline monitoring and leak detection is actually so hard and so difficult. But so to start, we want to make sure that we are supporting the preferred sensor position, either whether that's done through a new build or if we're looking at retrofit type of environments. So why consider retrofitting? The key aspect to this and the key answer is, look, there's 2.5 million miles of transmission pipeline in the United States alone. And as towns and cities continue to grow and we have urban sprawl, we have what's called, municipal encroachment occurring quite a bit. Here's an example of this map showing the small town and what was previously a farmer's field having municipal growth or sprawl or encroachment onto what were potentially unknown rights of way for existing and potentially new pipelines. So we see this area of future development here where these houses are going to be expanding. Before they know it, they're going to be essentially on the back door of an existing pipeline right of way. So these create all kinds of potential integrity risks of having population zones moving into these potentially areas where there might be aging assets. So distributed fiber optic sensing then becomes a very complementary approach to other monitoring capabilities that are consistent with API 1175 practices around program and portfolio management for leak detection. Adding DFOS to those existing pipelines can potentially extend the assets and is obviously a much less costly situation than potentially rebuilding those assets. And actually, this is a really important part. It fits very, very well to ongoing environmental, social, and governance strategies and scorecards. So this is whole movement largely driven from investment community around what's called ESG and ensuring that pipeline operators specifically here are actually doing things to progress their ESG scorecards and providing benefit over time. And a big part of that includes pipeline safety and integrity. Big other aspect of big trends that we're going to talk a little bit more about here include the accuracy of machines and other technologies and methods used to either locate and survey the pipe, as well as deploy fiber sensors and conduit. These are becoming much more advanced and much more mature, and we can really use these type of technologies to be more relevant and help us with retrofitting type of deployments. Okay, so now we're going to move on to the first category of retrofitting, which we call external retrofitting. So listen, there's a lot of detail on this slide. I've got a number of supporting materials that are going to be showing on upcoming slides. But with new technologies that are better able to find the pipeline asset itself, the conduit for fiber sensor can be placed very, very close or sufficiently close for effective distributed fiber optic sensing. Now, we really need to be balancing here the need to be close to the pipe for effective sensing and balance that against safety requirements. Obviously, we want to avoid the risk of potentially damaging the pipe by investing in this technology to maintain the ongoing longevity of that pipe. There's also the aspect that we're always going to be trying to find the balance. We're going to be talking about this throughout the rest of the presentation on fiber sensor proximity, again, being very close to the asset that we want, versus fiber continuity, particularly long distance fiber continuity. If we're talking about very long distance pipelines, we don't have unnecessary hardware just because we weren't able to achieve continuity. This is a great image here that FOSA has let me borrow. We can actually see this representing ultimately the objectives that we're trying to accomplish, where we've got a pipe deployed largely in an open cut type of an environment, and we've got these additional conduits here. And in fact, we've got two showing fiber optics in those conduits that then can be used to monitor. And the very interesting of this image is showing those just being offset. We'll say, and we're going to say this quite a bit, based on our experience, around a meter away, call it around the 3 o'clock position of that pipe. We've been meeting and working with pipeline operators, technology developers, machine manufacturers, distributors of those machine manufacturers, and of course construction contractors, all in the basis of trying to find the right approaches to retrofitting. And our experience has been, as I'd mentioned, that the optimal distance is really about 1 meter away from that pipe and a near field pipe kind of deployment for sensing and deployment safety. And this is very consistent, of course, with the 116.2 rule that applies to pipeline safety. And a shout out to our investor with Enbridge reminding me about some great materials around this. And just to explain that, the 116.2 means at 100 feet, any activity around a pipeline right-of-way at surface needs to have locating done before any activity is actually performed. 16 means 16 feet of any mechanical excavation, around 16 feet of any buried facility or pipeline must have a positive locate identification done in advance, of course, but also have an inspector present during that activity. And then the 2 foot is no mechanical excavation within 2 feet of a buried pipeline or facility at any time. So in other words, have to be hand digging or used hydrovacing that prevents essentially backhoes from being inside what we call the exclusion zones. Now, a variety of approaches are becoming much more relevant. Number one, by using existing locating staff who've been doing their job for many years, finding utilities, finding pipes that are already been deployed. Confirming that actual pipe location then becomes an important aspect. You're going to see us talk a little bit about using periodic bell holes and doing that, and surveying ultimately the expected pipe position upon various points of the right-of-way. It's important to note that as-built records are really important to integrate here. The newer the pipe, if it's 10 or 15 years old, the as-built records of that pipeline construction are certainly better than if they are 50 years old. You're about to see, the accuracy of both machinery and tools is also improving quite dramatically over the past number of years to be able to support the deployment of where we want that fiber sensor positioned. And then we're going to talk a little bit about trenchless crossings. It is a challenge, and what some of the new best practices are to be able to balance off proximity and continuity. And what we should also point out with these capabilities is the economics are becoming much more reasonable and are becoming much more effective in terms of justifying the deployment. So I'll start just with some images here of approaches with handheld technologies and resources. Certainly, professionals like this with pipeline companies have been using processes and technology for very effectively over the past years to find utilities and pipes below. Obviously, the call before you dig is the example here. It's not just simple metal detectors. They're looking for tracer wire, new uses of ground penetrating radar, ultrasound, very high accuracy, centimeter level GPS for survey techniques are all being used and used very, very effectively. And so instead of reinventing the wheel, we really want to leverage these resources with high accuracy tools to be much more of a reality of effectively finding that pipe. The goal here is to accurately know where the existing pipe is, and then able to render an accurate 3D mapping file integrated with the as-built records of the pipeline itself with survey and locate data, and then being able to use that 3D mapping file for conduit placement machinery. So this is an example of some of the new machines, not necessarily new actually, but just approaches with advances in the technology around some of the machines that are out there. New machine automation can really leverage that accurate 3D mapping file to place conduit in the exact position that we desire. Let's say the near field 3 o'clock position around 1 meter away from the pipe. And so again, we're also looking at different types of technologies that are being integrated here. They also include things like ground penetrating radar with these machines, ultrasound, again, high accuracy GPS, which includes actually things like inertial compensation for tilt. Construction machines, precision agriculture machines have used these types of technologies for many, many years. And inclusive of plow or the blade management technologies, whether it be angle or swivels of those types of implements. So a variety of different types of machines, and I appreciate a lot of these images here are very plow oriented. Although hydrovacing advancements are also very, very relevant. You can actually see in the lower right-hand corner illustration of a hydrovac, and you actually see a kind of a survey line that's been painted that they are typically looking, in this case, looking likely to build a bell hole. We'll talk a little about that here shortly, but all these types of machines using that integrated mapping file can be used to be able to accurately place the conduit where we want it. Now, I mentioned these are largely plows. What I've actually got next here to show you a little bit more in action, and some video credit here to another FOSA member, Network Integrity Systems, showing a vibratory plow. And so you can actually see this yellow plow. It's got a lead here and a blade inside that's digging into the ground, and just on the very, very top here, it's actually placing a direct burial fiber optic cable. So if I just run this may be very clunky, but I'm going to see if it works anyway on your screens. So as you can see here, Plow is going along the path design and actually creating a fiber optic cable as it goes. Now, this is a very small scale example. You can see it was done along this fence line, but the actual concept remains the same, even if it is a much larger machine that's being used. So another way to sort of visualize this external retrofitting is this sort of open cut approach. Nice little diagram here showing, a pipeline right of way, a couple pipes in the trench, and you can actually see we've got municipal encroachment on this pipeline right of way. And so as we look at this, let's assume that we've now had our locating team out and have actually mapped the right of way itself. And then we're actually going to deploy these hydrovac-based bell holes. These can be used to utilize the precision nature of the machines to actually visualize more specifically with confirmation of where the pipe is based on those records. And again, we can actually use that those bell holes as place points along that 3D mapping file to actually place that conduit in the exact position that we want, both on the first pipe and then on the second pipe. And you notice actually the second pipe has a bit of a turn from the as-built records that we can map into the deployment technique, and that ensure that we are hanging at the exact desired distance and clock position on that pipeline. Now, one of the key aspects here are these bell holes, and the economic benefit will be: do we use these more conservatively in terms of hydrovacing these bell holes at certain distances, or maybe we don't need the second hole on this example. And that allows us to reduce the overall construction costs and the hydrovacing of those bell holes in the first place. Just some examples of bell holes. Hydrovacs have used these as a technique with pipeline integrity for many years. In fact, they're called integrity digs to be able to access the pipe to inspect either the coating or otherwise in the integrity aspect of the pipe itself. In fact, pipeline dig programs could be very well leveraged to plan out some of these retrofitting schemes. You can actually visualize by some of these pictures, and some of these are much deeper. These are much a larger integrity dig type of examples. But other than this left-hand one, which is a little smaller, more the bell hole that we're talking about. But you can actually think about it, visualizing with the naked eye how you could link these together with bell holes to become much more comfortable where the pipe actually is against a 3D mapped file. And while using more advanced survey techniques along with as-built records can generate a very accurate plot of trenching between these bell holes, using these becomes a more conservative factor. And again, the distance between those bell holes will have a big part of the economic impact. Also want to talk a little bit about horizontal directional considerations. Again, there's always this balance of attempting to maintain a proximity of the fiber close to the pipe with continuity of that fiber to ensure long distance sensing. Now, a little bit about horizontal directional drilling. These are used for sort of trenchless crossings where typically a directional drill is drilling a bore path, bore hole with very high accuracy actually on the vertical scale for that drill bit. And then once the bore path has been properly configured, and that could be across different existing services, pipelines, or utilities. And again, this has been done for years. Then there's what's called the pullback procedure, where pipe is actually pulled back through that borehole path that was dug. Now, as we look at providing continuity, the best practice we believe is here to bore a new HDD for the conduit, but actually wide of the short distances that we're looking at, and then reacquire proximity on either side of the pole. So in this river crossing, as an example, reacquire proximity on either side. And so again, there's always this trade-off of proximity versus continuity, and where we want to have short distance not be compromised for continuity over proximity. So you can see here in the example that we've shown, it makes it look like the conduit has been pulled deeper, but you can think about it flanking wide across crossings where we can then reacquire proximity on either side of the riverbank. And we hope this actually will change over time with improved left or right or X and Y accuracy of directional drilling. We also want to talk about above ground external retrofitting. There's lots of pipe that looks like images here that can be retrofitted. Obviously, above ground is much less complex, much less machine oriented and more labor oriented. There are challenges to manage through though, including the environmental side of things, weather impact through sunlight, creating intense heat, and then going behind clouds, we'll have that heat dissipate, wind. Those are all aspects that need to be factored in. So as a result, we typically prefer to have conduit placement below the pipe and these types of aerial type of retrofitting examples. And then we can really effectively use our machine learning algorithms to really filter out those potential weather impacts. Again, things like wind interference and otherwise sun heating that may be relevant for an above ground type of pipeline section. Okay, so that was external retrofitting. The other topic we're going to get into here then becomes internal retrofitting. And again, plenty of details on the slides. More supporting materials will be shown in upcoming slides. What internal retrofitting does for deployment means is essentially taking distributed fiber optic sensing and deploying it inside the pipe. Now, this is typically relevant for more short, what are called high consequence areas. This could be river crossings, environmental zones. We actually are working on a project right now where it's being contemplated to go under an eagle nesting habitat or otherwise populated areas. Also less machine oriented, a little bit more labor oriented, but the concept is using the fiber optic sensor typically installed inside a stainless steel capillary tube first, and then using both a toe pig and an injector system to really push and pull that fiber optic sensor into the appropriate place. We've learned that low profile of the capillary tube doesn't actually compromise flow. We've been down to fairly small pipes in testing this off. But some of the challenges and considerations that we've learned along the way is, number one, understanding the ingress options. How do we get inside the pipe? How do we deal with valves? How do we manage and install pack-off assemblies to actually maintain pressure and safety? How do we deal with running pigs that may be running off? And the answer on that is looking at potentially customized pigs that can coexist with the fiber sensor rather than retracting it every time. And then long distances. This is really for shorter, high consequence areas. Literally the weight of the cable and the stainless steel tube makes it more difficult for deployment of longer distances through the toe pig approach and procedure. The first question, of course, how do we get the fiber optic sensor inside the pipe? And there's a couple different ways that we can think about ingressing that pipe. One is actually using a pig launching station. Here's an example actually where we got what's called a pack off installed around a flange going into a pig launching barrel. And that allows us as an ingress point to be able to pull that fiber optic sensing sensor in the cap tube through that assembly and into the pipe. The other is just to weld on or tap on a 45-degree ingress point, which again would then be equipped with a pack-off assembly, essentially creating a safety seal and valve capability in that ingress portion of that pipe. Once we've selected that, then the installation procedure, in this case, we are again using that sort of pig launching barrel access point, where we got the stainless steel tubing coming through the pack-off assembly. Then we'd actually attach that to a toe pig. And that toe pig will actually then have, with pressure involved on the line, pull that line into place. We'll also use an injector for traction control to push the line into place. Once that is at its desired distance, then we have a disengagement system of that toe pig that clicks into place. The line then will fall into the place in the desired distance, and the toe pig itself will then get caught in the next available pig catching station. So this is obviously an animated cartoon of this, or not animated, but illustration of this. This is an example of the exact assembly that we recently did this past winter in Saskatchewan. We've outlined kind of the procedures around doing this. Obviously, we need to be mindful of safety around pipelines. This does very much leverage downhole injection type procedures for conventional oil and gas wells. Really, regardless of the ingress point alternative, the procedure is very much the same, where we're first mounting the flange and preparing the injection configuration, including that toe pig and disconnect system. And then as that injection process occurs, we're opening valves and using flow and pressure from the pipeline itself to move that toe pig at a control speed, and then invoke the release mechanism when we hit the desired distance. Then we've also had a procedure, of course, to retract that cable for a variety of reasons. Maybe it's to remove for inline inspection purposes, but the ability to use a reel system. You can see actually the reel here on the example lower right-hand corner, to control the retraction of that fiber optic sensor and make sure we're managing all the proper valves and pack-offs, so we're not creating any sort of pressure changes or otherwise creating any sort of safety incident. And then we can turn the pipeline back over to the operator. For a distance of 2 to 4 kilometers, this can take about a half an hour to 45 minutes to remove the actual sensor itself to align to the timing required for inline inspection tools. Here's some examples. Here's a toe pig with a release assembly. Here's the example of being in this remote location with a spooling system on a trailer. You can see the fiber optic stainless steel cap tube sensor system that's being used here as part of this deployment. Internal stainless steel internal deployment obviously relies on stainless steel tubing, various sizes depending on the robustness that's required here. There may be situations where going through the valve is necessary. You can see there's an image here where, despite safety precautions, we may need to leverage that robustness if a valve get accidentally closed. Stainless steel also makes a great sensor conduit itself, but there are considerations to think about in using stainless steel in terms of the forces that may be on it, both through the pack-off assembly, the weight of the tubing itself, any kind of residual bending or helicking of the sensor as it's inside the pipe, and of course any pipeline bends itself. And then ultimately we're trying to balance the objectives here of having the robustness of the stainless steel cap tube be strong enough to withstand some of the pressures and pressure differentials that it may be impacted by, but also be able to properly yield at a point where we want that release mechanism to work for the toe pig. Here's just a few more examples of field deployments using internal deployment. Again, by the way, not all pipelines are blue, but we do have this pig launching station as the ingress point in the pack-off assembly, and the toe pig that was actually used to pull that fiber optic sensor into place at that location. In this case, in the location, we've got more of a 45-degree ingress point and a foam-based pig that was pulled into, in this case, a water line. So now that we've retrofitted, whether that's internal or external, how well does it work? How well does the data actually perform? The first thing we do, no matter what type of deployment that we're using, is the characterizing of the baseline. What is normal of the pipeline activity? And so we do that with a variety of different tests to look for ambient activities that could be normal, whether that be flow changes, vehicle traffic, train traffic, or otherwise sort of activities that are normal on the pipeline right of way. And then also differentiate that from abnormal activities that may be unexpected valves opening and closing, excessive strain from geotechnical activity, earthquakes or landslides, security intrusion attempts, accidental or otherwise, and then of course leaks. And so we actually feel that there's the best practice is to properly simulate baselining, leaks during baselining. That really helps train the system to alarm and also suppress any other false positive type conditions. We don't want to be alarming on things that are normal with the pipeline. And so it's really good practice to train a system with this leak simulation apparatus. You can see where we've used it with a downhole nozzle that we can use at various sizes and pressures to simulate different leaks by blowing gas or liquids down onto the hose pipe below that's being monitored. Here's a couple data examples to show as we start to move towards closing here, where we are actually able to show, in this case, just baselining examples of above ground driving tests up and down the right of way. In this case, we do have both internally and externally deployed sensors for great reference. In fact, they're here sort of illustrated over top of each other and represented by different channels along the pipeline itself. We can also augment this with ground-based intrusion tests and tap tests. and walking the line. This actually helps us to effectively figure out the offset distance when we're using external sensors, whether they're retrofitted or deployed during construction. And again, using that leak simulation nozzle assembly as a reference is a great way to continue baselining. This is an example of ground disturbance testing at various locations and distances away from the pipeline. And again, we've got internally and externally deployed sensors, and you can see just the signal to noise ratio on comparatively internal versus external fiber, and how both are very effective at picking up all of the different simulated tests, specifically on this right-of-way that we've done with various machinery. Leak detection, of course, a big aspect to testing the different types of deployments. This one, again, is an internal deployment that we used with a water pipeline. What was great was that we were actually monitoring flow of the pipeline while leaks were actually physically created and released. So very blind-oriented testing, I should say, and one that was great given it was a water line, in that they could actually create real leaks into the environment, which obviously is not possible to do in the field with a hydrocarbon-based line. Great leak signatures here, which are characterized, and you can see a big water hammer effect, and from the vibration and strain on the pipe during the initiation of those leaks. And then you can see some of the frequency aspects and the broadband signatures from an acoustics perspective to correlate to those leaks as well. Here's a variety of other examples. Again, internally deployed sensors on a variety of different simulated leaks. This is not the water example that I just referenced, but different nozzle sizes, all kinds of different pressure points. And you can see just from an acoustic plot here how well that each of those different tests are picked up, even with the internal sensor deployed. And then finally, this is an example of leak simulated from with a external pipeline, an external retrofit of a pipeline. We're about 1 meter away from the pipe in this case. Again, you can see very good acoustic response from frequency and strain of the pipe that are well correlated to the initiation of the leak itself. We typically then push these types of events and data through what we call our HCS monitor user and control room software interface. It can be used for operators and analysts to accommodate various event detection, leak alarms, or other events, and other value-added applications. These screenshotted illustrations actually include an illustration of our recently announced pipeline pig management application, or PMA, where you can see where pigs can be tracked on various pipes. Data and analysis can be provided through the interface in real time, and then even alarms can be generated for examples, as we have here, where the pig is actually stopped inside the pipe. So, in summary, based on new technology advances, retrofitting distributed fiber optic sensing for existing pipeline is becoming much more of a reality, both external to the pipe and internal to the pipe. The external retrofit is slightly more expensive compared to new builds, but a very effective and a reasonable way to address aging pipelines, and the economics are becoming much more favorable as time progresses here. With our experience, leveraging those technologies to locate the pipe and accurately place that conduit or cable are becoming much more mature, so we can find that sweet spot of around 1 meter away, 3 o'clock position, which we believe is the optimal location for retrofit sensing. And then internal deployment is also proven to be a very effective way for shorter, high consequence area retrofitting. Again, very beneficial where trench deployment is just not an option. Requires using and monitoring a pack-off assembly as an ingress point, and then use of a tow pig and injector system to properly insert the fiber optic sensor in a stainless steel capillary line. Some challenges do remain around retraction deployment. We do have procedures around doing that with significant runs of cleaning pigs. We're actually working through solutions that may include custom designed pigs that would permit the coexistence of the fiber sensor while the pig kind of passes through. And with both approaches to retrofitting on existing pipelines, they can extend the useful asset of those pipelines. Is a much less costly alternative than rebuilding. It fits very, very well into pipeline integrity and ESG-oriented strategies and scorecards. So we believe with the 2.5 million miles of transmission pipeline in the US alone, that retrofitting is going to become more and more important to the industry over the coming years. Just want to end with illustration and thanks to a number of the great partners that we work with. This is a subset, and they obviously range from predominantly oil and gas related pipeline operators, but also include non-hydrocarbon based pipeline operators, as well as in mining and water utilities as well. And with that, I thank you. Mark, I'll turn it back over to you for any potential questions that might be. If I'm not able to, or we don't get to all questions today, feel free to email me at the information on the screen, and we'll get back to you in short order.
Well, we do have quite a few questions, and a number of them picked off on the internal, and some questions about. I think there was a little confusion about pigging, whether or not conventional pigs can be used, or is it simply a question that there's a preference for using more specialized pigging?
Great question, and so we should talk a little bit about, to answer that question. There's pigs and there's pigs, right? So there are inline inspection tools, which typically are run periodically. Let's say on a gas line, they're going to run them maybe once a year, and they're obviously quite involved pieces of machinery. For those inline inspection tool-based pigs, our proposal would be we actually run that retraction procedure. So we actually remove the line from the place, we run the inline inspection tools, and then we actually reinsert the fiber optic sensor after the pig run has been completed. And again, for examples where you're running that once a year, that's not all that involved, not that expensive, and quite reasonable. Now, on a heavy oil line that might be running cleaning pigs, much more often than that, even every 2 weeks, it may not be as logistically practical, of course, to retract. And so that is the one sort of downside that we're working through, one of the challenges. And as I mentioned, that's the idea of where we are looking at where custom cleaning pig designs may have may have slots that may be octagonal in design that would allow that pig to actually coexist with the fiber sensor in place, and actually still run the effective cleaning procedure that it's intended to do.
Following up with a related question, can internal install detect leaks for multiple pipelines in obviously a multiple pipeline right away?
Yeah, I mean, that's a difficult one to answer, given that needing to assess what that might look like. We've certainly seen very closely tied together pipes in a common trench, maybe separated by inches, not meters. And in cases like that, depending on the flow and the pressure profile, the product type, if there were say 3 pipes in a trench and we were internally deployed on the middle pipe, and there was a leak event in one of the other 2 pipes, the answer is it's quite likely we would actually be able to detect that incident itself, as well as having that common sensor for multiple pipes in the trench. We can pick up more right-of-way type of activities as well, right? The intrusion testing that we showed there was a really good example. If there was digging too close to that pipeline right-of-way, then the operator was comfortable, we could alarm that event through the single sensor that might not be deployed inside every single one of those pipes in the same right-of-way.
And now doing an external question, can a external retrofit detect air pockets in a line?
Well, certainly, I mean, so this is independent of retrofitting. Certainly we find with, say, on the pipe deployment, which is most of what we do, our ability to detect all kinds of different flow anomalies, batch changes, density changes of flow, multi-phase flows, is actually very effective. And so independent of retrofitting, the answer is yes, we can detect all kinds of different elements of flow that may be specific to air bubbles or other aspects of flow. In fact, we have a patent that was awarded to us about a year ago around using distributed fiber optic sensing for flow monitoring. And it's one of those other sort of value-added applications that we're very keen on commercializing down the road.
Now, next question is, I know you referenced a number of your partners, but the question was, do you guys do the trenching or do you work with partners, or kind of where does Hifi fit into that, into this process?
Yeah, great question. I mean, so as I said at the outset, we're a technology company, but very focused on pipelines. So we've had to learn, vernacular approaches and procedures around being a pipeliner. We're not a construction company. We're not a field service company. We do typically work with general contractors on any deployment, whether it's retrofitting or otherwise, around procedures, specifications. We have lots of documentation and training around conduit placement. And then we or our other partners can actually do the fiber injection, whether that's through air injection or liquid injection of the fiber cables. But directly back to your question, no, we're not a construction contractor, but we work pretty intimately with construction contractors that would be involved in either building new pipe or retrofitting pipe with some of those machines and capabilities that were referenced in the presentation.
And I guess here's a kind of a softball question, but one of our questioners asked about using this for natural gas pipelines. So I guess we can probably elaborate, or how shall I say, clarify that particular point.
Yeah, well, many of the pipes you saw in images in the presentation are examples of natural gas lines. Now, more transmission lines. I don't know if the question gets down to thinking about more distribution lines. And the answer is yes. I mean, any product under pressure in a tubular, whether that tube is a 48-inch tube or a 3-inch tube, is what we're all about in terms of monitoring for event detection, flow monitoring, etc. So it definitely works. We are product agnostic. A lot of what we do is obviously liquids, but we do a lot of gas work and water as well, whether that be potable water, wastewater, etc.
And let me just follow up. I guess the add-on question would be, obviously gathering lines would also be potential applications as well.
Yeah, we have done gathering line deployments as well.
Great. Well, that takes us to the end of our questions. I will say the normal questions that we do regularly get are, will the PowerPoint be available? And the answer is yes. We will have this presentation loaded on the FOSA YouTube page or channel, I should say, relatively quickly, and people will be able to follow up with that and see what they maybe perhaps drill down a little bit more. But also we have Steve's contact information for those people who want to ask him some questions directly. Steve, thank you very much. It's a very informative presentation.
Thanks, Mark. We're really excited about the opportunity here. We've actually working with, in planning stages, around 250 kilometers of pipeline retrofitting projects. I should have said that earlier. And so obviously it's going to be a big part of our future, and we're very excited to be part of it.